Hello and welcome back. In the previous lecture, we tried to understand how a mixture of chemical species behave or how we can calculate thermodynamic properties for a mixture of chemical species. In today's lecture, we start working with what are known as excess properties. But before we do that, as usual, let us quickly recap what we have done so far in this section. In a mixture of chemical species, we have defined a quantity known as the partial molar property, Mi bar, right? And then we have related it to the total property of the mixture via the summability relation weighted with the mole fraction of that particular species. And then we have interdependency among various thermodynamic properties in terms of partial molar properties, such as Gi bar, which we also call as chemical potential, by the way, was Hi bar minus Ts bar, similar to G is H minus Ts and so on. And in addition, the change in this property dGi bar is at constant composition is Vi bar dP minus Si bar dt. This is similar to dG is VdP minus SdT. In addition to these relationships amongst the partial molar properties, we also had interdependency via the Gibbs-Duhem equation, which reads Xi dmi bar, or summation of Xi dmi bar is 0 at constant temperature and pressure. So in that sense, in a binary mixture, M1 bar and M2 bar are going to be related to one another. Once we identified these relationships, we went on to look at how a mixture or how the partial molar properties in a mixture themselves are going to be related to the properties of the pure species, or in other words, how Mi bar is going to be related to Mi. And we worked our way through this by first considering ideal gas mixtures, wherein we said for an ideal gas mixture, the molar volume or the partial molar volume and the partial molar enthalpy are going to be same as the pure component values, and hence in a mixture Vig, V for the mixture is going to be same as Vi bar Ig, and H for the mixture is going to be summation of Yi Hi bar Ig, so this will be summation of Yi Hi, right? And for entropy and Gibbs free energy, however, there are going to be additional terms. These are the additional terms in addition to the pure component values SiIg and GiIg. And we also defined quantities known as the property changes upon mixing, and for ideal gases, the property change upon mixing for volume and enthalpy are 0, whereas they are not 0 for entropy change upon mixing and Gibbs free energy change upon mixing. Once we know the mole fractions, we can calculate these quantities. This is for an ideal gas mixture, and we said we're going to define ideal solution such that it behaves in a similar fashion, or the Gibbs free energy change upon mixing, or rather the partial molar Gibbs free energy change, whichever way we want to look at it, is going to be related to the pure species Gibbs free energy through a similar equation as that in case of an ideal gas. For example, in an ideal gas, Gi bar Ig is plus RT ln Yi, and we said in an ideal solution, Gi bar Id is going to be related through an analogous equation, Gi plus RT ln Xi. This ideal solution can be applied to dense phases, dense gases, or liquids as well. The only requirement is that the partial molar Gibbs free energy for species I, for each species I in the mixture, is related to the pure component Gibbs free energy via this equation. And once that happens, it turns out all the property changes upon mixing we have identified for ideal gas mixtures are going to be same for ideal solutions also. The only difference is that these are not ideal gases, they can be dense phases, liquid phases, but as long as this property is satisfied, then all the property changes upon mixing are going to be exactly same as in case of an ideal gas mixture. Now, of course, in real life, we will not have ideal solutions always. Ideal solutions occur, as we said, when we have molecular species or the constituents of the mixture. If the constituents of the mixture have all the species in the mixture have similar molecular size and similar chemical nature. For example, adjacent species in a homologous series or isomers, etc., where they are likely to occur. On the other hand, real mixtures can be non-ideal, just like we have ideal gases and non-ideal gases. We can have mixtures which do not form ideal solutions. Then how do we quantify such mixtures? We're going to resort to a similar exercise as we have done for real gases. For real gases, recall that we have identified a property known as residual property, which is the difference between the property of the real gas minus that of the ideal gas. So this property, in a sense, indicates how far away from ideality we are. So we're going to define a similar property so that we identify the deviation from an ideal solution. This property is known as excess property. We define excess property M, E being the excess property, as M, the property of the solution, minus the property in an ideal solution. This M can be anything. For example, it can be Gibbs free energy. So GE is going to be G minus G ideal, any thermodynamic property. Or HE, the excess enthalpy, is going to be H minus H ideal. The excess volume is going to be V minus V ideal, and so on. And of course, SE, let's write that also, is S minus S for the ideal solution. Now, if you recall, H for the ideal solution is sigma Xi Hi bar Id. This is the summability relation. And in an ideal solution, Hi bar Id is same as Xi Hi for the pure species. So that implies He is going to be H minus sigma Xi Hi by definition. And recall that this quantity, we have also called it as delta H mixing. So in that sense, He is going to be exactly identical to delta H mixing. And similarly, VE is going to be exactly identical to delta V mixing. This is because V for an ideal is also sigma Xi Vi. But GE and SE, of course, are not going to follow this follow these relationships. They are simply G minus G ideal and S minus S ideal. So we have identified excess properties now. These are defined as the differences between the property and that of a property of an ideal solution. Let's also try to get some relationships with respect to excess properties. And what we'll do is we will try to identify commonality in the relationships between the total properties, the residual properties, and excess properties, so that it is easy to comprehend all the three of them put together. But before we do that, let's quickly derive the fundamental property relationship based on Gibbs free energy one more time. The fundamental property relation in terms of Gibbs free energy, if I want to write d Ng over RT, then it will be d of Ng 1 over RT minus Ng by RT square dt. And for an open system, if you recall, dNg is Nv dP minus Ns dt plus sigma mu I dNi. What I'll do is I'll use this relation in the first equation so that I get d of Ng over RT is going to be 1 over RT Nv dP minus Ns dt plus sigma over I mu I dNi minus Ng by RT square dt is the last term. We'll simplify this. what we get is NV over RT dP minus N times Ts plus Ng, all of it over RT square dt plus 1 over RT sigma of mu I d Ni. Right. And if you notice, N times Ts plus Ng is N of G plus Ts, and because G is H minus Ts, this will turn out to be NH. So what I can do is substitute NH here. So this will turn out to be NV by RT dP minus NH by RT square dt plus sigma over I. I'm going to replace chemical potential with partial molar Gibbs free energy. Both are identical, dNi. And this is the quantity d of Ng over RT. This is going to be our fundamental property relationship in terms of G as the generating function. So we'll take this relation, d of Ng over RT is NV by RT dP minus NH by RT square dt plus sigma over I GI bar by RT dNi. Once we look at this relationship, a few derivatives need to be easily written. Derivative of Ng over RT with respect to the pressure at constant T and Ni is going to be NV over RT. Right, we are holding T constant and we are holding Ni constant, so both these terms disappear and the derivative will turn out to be NV over RT. Similarly, derivative of Ng over RT with respect to temperature at constant P and Ni is going to be negative NH by RT square. In this case, we are holding the pressure constant, so this term disappears, and Ni constant, so this term disappears. All Ni, in fact, constant, so this term disappears, and we have negative NH by RT square. And finally, derivative of Ng over RT with respect to Ni when I hold the temperature, pressure, and all the Nj's that are not equal to I constant will be Gi bar by RT, which essentially is the definition for the partial molar Gibbs free energy anyway. So these are the three derivatives one can easily write looking at this equation. What we can also do is write this equation for an ideal gas. Ngig by RT is Nvig by RT dP minus Nhig by RT square dt plus sigma Gi bar Ig by RT dNi. I can subtract one from the other so that I get d of Ngr by RT. This is the residual Gibbs free energy. If you recall, the definition of residual Gibbs free energy is G minus Gig, is Nvr by RT dP minus Nhr by RT square dt plus sigma Gi bar R by RT dNi. Right? So now if I look at equation 3, I can easily write again these equations. Derivative of Ngr by RT over pressure at constant T and Ni, or T and X. If Ni is constant, the composition X itself is constant, is going to be Nvr by RT. Now compare this equation with the one for the total property. These are identical except that I have replaced the total property M with residual property Mr. Similarly, derivative of Ngr by RT with respect to T at constant P and Ni is going to be negative Nhr by RT square. And finally, derivative of Ngr by RT with respect to Ni is going to be Gi bar R the partial molar residual Gibbs free energy GI bar R over RT. This is the scenario for the residual properties. What we can do is we can also take and write similar expressions for excess properties. We'll start with the fundamental relation, property relation, dNg by RT is NV by RT dP minus NH by RT square dt plus sigma GI bar by RT dNi. And I can write it for an ideal solution also. It will be NVID by RT dP minus NHID by RT square dt plus sigma GI bar by RT for ideal solution dNi. I subtract one from the other. What I get is dNGE by RT. The excess Gibbs free energy is going to be related to the excess volume times dP excess enthalpy dt plus sigma GI bar E by RT dNi. GI bar E being the partial molar excess Gibbs free energy. Now compare this equation for excess property with the previous equation for residual property. The equations look identical. The excess property simply needs to be replaced with the residual property. And as in this case, I can again write all the derivatives we have written earlier. The derivative of excess Gibbs free energy over pressure at constant temperature and Ni is going to be NVE by RT. Its derivative NGE by RT with respect to temperature at constant pressure and Ni is going to be negative NHE by RT square. And finally, the derivative of GE by RT with respect to Ni at PT and Nj is going to be negative it's going to be GI bar E by RT. So again, these relationships are exactly identical to the ones in residual properties or the total properties. Just want to make one final comment before we end this discussion on the similarities between M, ME, and MR in terms of fundamental property relations. Let's use another slide. In any of these cases, if you look at it, we said the derivative of NGE by RT, we'll take one example with respect to temperature, let's say, at P and Ni is negative NHE by RT square. Now, if you look at this, what I'm holding constant when I take the derivative on the left-hand side is the pressure, of course, and Ni. Ni being all species I, or the moles of all species I are held constant. If moles of all species I are held constant, N, if Ni is constant, then N, which is summation of Ni, will also be constant. If N is constant, then this can come out of the derivative here, right? And on this side also I have N. So that will cancel out. N times derivative of GE by RT over dou T. And because Ni is constant, Xi is also constant. Ni is constant, N is constant, so Xi, the mole fraction, needs to be constant. So instead of calling it as at constant Ni, we can also say it is at constant X will be negative NHE by RT square. And N on both sides can be omitted. So what I have in effect is the derivative of GE over RT at constant temperature, with respect to temperature at constant pressure and mole fraction is going to be equal to negative He by RT squared. So I can use this fundamental property relation and also write the dependencies of molar properties themselves. I don't have to use the total property all the time. The only place where total property needs to be used is when we define the partial molar properties. So for example, in the last equation here, one of the ni's is changing, all the other nj's are constant. Over here, I cannot say that n is constant because one of the ni's is changing. But in the first two equations, when all the ni's are constant, I can write that equation either for the total property or the molar property, right? So that is the takeaway from this particular exercise. We can write the fundamental property relation with Gibbs free energy as the generating function, and the total property, the residual property, as well as the excess property all follow analogous relationships. Now, in addition to this, there are other auxiliary properties one can define in terms of excess properties, right? For example, if you recall, right, Cp was derivative of H with respect to temperature at constant pressure, and in a multi-component mixture, not just pressure, even the mole fraction for that mixture needs to be held constant. This is the definition for the specific heat capacity Cp. One can write it for an ideal solution, derivative of H for the ideal solution over derivative of temperature at constant P and X, and Cpe will then be derivative for the excess enthalpy with respect to temperature at constant P and X. So this is called as the heat excess specific heat capacity at constant pressure. We can write similar relationships as we did earlier for specific heat capacity. Now, having said this, what we have done then is we have identified a relationship between the property, right? What we have so far is we have identified a relationship between mi bar and m, that's a summability relation, and we have also identified a relationship between mi bar and mi for ideal solutions or mixture of ideal gases. So I know how mi bar is related to mi for ideal solutions. In addition, we have also defined a quantity known as the excess quantity, which is m minus m ideal. So me will be 0 for all ideal solutions because of this definition. And if the solution is non-ideal, me is not going to be 0 for non-ideal solutions, right? Or at least some of the me's are not going to be 0 for non-ideal solutions. Then the next thing we want to do is, there were ideal gases and then we have non-ideal gases. We have defined residual properties to characterize non-ideal gases, and we used equation of state, Pitzer correlations or Lee-Kessler tables, etc., to obtain residual properties. Similarly, how does one obtain excess properties? If I have an ideal solution and if I want to quantify thermodynamic properties, then to quantify thermodynamic properties in non-ideal solutions, we need some information about the excess properties if we are going to take this route. So how does one get excess properties? For most of our cases in chemical engineering applications, we're going to use Gibbs free energy as our generating function. So what we are interested in is obtaining excess Gibbs free energy. So then we are looking for models for excess Gibbs free energy. So usually it turns out that the excess Gibbs free energy data, GE, is obtained from experiments and typically from VLE experiments or vapor liquid equilibrium experiments. Okay. And HE, if you recall, is the excess enthalpy, and we also said because of the property of ideal solutions, HE will also be same as delta H mixing or the enthalpy change upon mixing. So HE is usually obtained from mixing experiments. Once we have GE and HE, we can readily calculate SE from the relation GE is HE minus TSE. So we have GE and HE, so we can calculate SE, the excess entropy. This is the usual route that is followed to get the excess properties. How do these excess properties, can we broadly talk about how these excess properties are going to behave? Let's see. Let's consider a binary system for this discussion. We have two components, and the mole fractions of the two components are x1 and x2. And at the limit of x1 going to 1, right, m, any thermodynamic property m, if you recall, we said is going to approach the pure component property m1. At this limit, m in an ideal solution also will approach m1, which implies at the pure component limit, the excess property will go to 0. This is true for all excess properties, right? And not just for pure component limit of 1. In fact, this logic should also hold for pure component limit of 2. The excess property should go to 0. Of course, at that limit, m will approach m2. MID will also approach m2, the pure component property of 2. Other than that, there is no particular thermodynamic restriction on how excess properties such as GE or HE need to behave. For example, GE can be greater than 0. Let's say this is 0. I have GE on y-axis and x1, this is a binary mixture, on x-axis going from 0 to 1, and GE is 0 at the horizontal line I have drawn there. So GE in some cases can be greater than 0. In some other cases, it can be less than 0. Usual experience says that it is parabolic in shape, but there can be variation. Of course, that's not a thermodynamic requirement, but mostly it is parabolic in shape. It can be greater than 0 or less than 0. It can show positive deviations from ideal solution behavior or negative deviations from ideal solution behavior. If we talk about HE, in relation to GE, HE can be greater than GE, HE can be less than GE. So I'm going to draw GE using the yellow curve there. Notice that at both the ends of pure component limits at x1 equal to 0 or x1 equal to 1, the excess property is going to 0. So this is, the yellow one is GE, GE for the yellow one. And with respect to GE, HE can be greater or it can be smaller than GE. It can, in fact, for a part of the composition, it can be positive, and for the other part, it can be negative, and so on. So with respect to GE, there can be a lot of variations in terms of HE. And of course, once we have GE and HE, SE has to obey the difference between GE and HE, right? SE was, as we said earlier, HE minus GE over temperature. So depending on that, SE is going to vary. So as you see, the only thermodynamic restriction is that at both the pure component limits, both GE and HE have to go to 0. Other than that, there can be a wide variety of shapes one can observe in terms of GE and HE. Although, like I said, the most common trend is that GE is parabolic in nature with respect to composition. Now, having looked at these shapes, the next question to ask is, if I want to quantify the excess properties or non-ideality in a solution, we need to somehow model the behavior of the Gibbs free energy or enthalpy. How does one do that? Like I said, the most common way is to obtain GE from vapor liquid equilibrium data. So in general, to be able to understand this whole scheme of things, we first need to look at vapor-liquid equilibrium, right, or phase equilibrium in general. So let's talk a little bit now about vapor-liquid equilibrium. And for this discussion, we're going to introduce a concept known as fugacity, and let us see the origin or the reason for this thermodynamic variable. If you recall, for vapor-liquid equilibrium, we said the requirement is that the chemical potential of the species need to be same, of each species needs to be same in both the phases. If we use the superscript V for vapor and L for liquid, and we have a binary mixture, then the chemical potential of 1 in the vapor phase needs to be equal to the chemical potential of 1 in the liquid phase. Similarly, the chemical potential of the species 2 in the vapor phase also needs to equal to chemical potential of species 2 in the vapor phase. One can write this chemical potentials. Instead of using chemical potentials, we can also say that the partial molar Gibbs free energies of 1 in the vapor and liquid phases need to be same. Partial molar Gibbs free energies of 2 in the vapor and liquid phases need to be same for vapor-liquid equilibrium. So somehow, to be able to characterize vapor-liquid equilibrium, we need to relate this chemical potential or partial molar Gibbs free energy in both the phases. Now, let's take a break here and go back to partial molar Gibbs free energy and see how it is related to the pure component property. Let's talk about an ideal gas mixture, and in an ideal gas mixture, if you recall, we said that the partial molar Gibbs free energy of species 1, or in general for species I, is related to the pure component Gibbs free energy Gi via this relation plus RT ln Yi. Now, if you recall, the derivative of Giig is Vi dP. This is at constant temperature. In general, it is VdP minus Si dt, but at constant temperature, this term drops out and it is simply Vi dP. This is dGig, right? And we can integrate this from 0 pressure, and we can rework this integral to get Giig is going to be some constant with respect to temperature for that species I plus R ln, RT rather, ln P. So what I'll do is I'll take this equation for Giig and substitute it back in this expression, so that what we get is an expression for Gi bar Ig as the constant plus RT ln Yi times P. This is an expression for partial molar Gibbs free energy of species I in an ideal gas mixture. Now, if we look at this equation for a minute and ask a question, what would be its value as pressure P goes to 0? At the 0 pressure limit, right, it turns out Gi bar Ig needs to go to negative infinity. Only then this equation is going to be satisfied. And recall Gi bar Ig is also same as the chemical potential mu Ig. So in general, either the Gibbs free energy or chemical potential tend towards negative infinity at the 0 pressure limit. Although by itself it is not a mathematical problem, chemical potential and partial molar Gibbs free energies are rather abstract variables one cannot easily relate to. So what we do is we'll try to use a variable which one can easily relate to when working with phase equilibrium problems rather than working with chemical potentials. And towards that end, what we will do is this. We'll take this expression for Gi bar Ig, and we said it is the constant plus RT ln Yip. This is true for an ideal gas mixture, right? But in general, even if we don't have an ideal gas, we will simply write GI bar as this constant plus RT ln Fi hat. So we're replacing YIP, which by the way is partial pressure, right? YIP is the partial pressure Pi. We are replacing that quantity Pi with a quantity known as Fi hat, and we'll call this Fi hat as fugacity of species I. And the hat on top represents that I is in a mixture. So this is fugacity of species I in a mixture. So the way we define fugacity of species I in a mixture is GI bar is this, or in more general terms, dGi bar is RT d ln Fi hat. This is a more general definition for fugacity of species I in a mixture. In addition to this, because we also need to define a boundary condition, if you will, and what we do is we'll say that limit of P going to 0, at this limit we will say that Fi hat will be equal to YIP. These two equations together define what we call as fugacity of species I. We'll come back in the next class and see how this fugacity of species can be used and how it is more convenient to use rather than working with chemical potentials. Thank you.